Okay, so fluid dynamics, part three. So buoyancy calculations. We talked about buoyancy in the previous lesson. So there's two type of calculations. One is how much cargo can the boat carry, and the second would be what is the apparent weight of a submerged object, which we'll do in the next slide. So how much cargo can the boat carry? And this is related to at my previous school we had a pool, and so we had a boat project in physics class, and the instructions for the students was the instructions were you can use cardboard and duct tape and paint and build a boat that can float a person. And I was blown away at how well the construction went. So this, I don't know, they had names for the boats. I forget what this one was. But the challenge was to actually, I brought in my kayak paddle, and the challenge was to paddle your boat across the pool. And it was a like Olympic-sized pool. This boat looked really good. They had little outriggers. This one, of course, broke, and I think Jose took a dunk right there. Um, and then, oh yeah, here's action shot. This was Jack, and he is definitely getting submerged here. But the reality is that the volume of the boats was pretty large, and the students could float in them. I wish I had more. I wish I had video. But there was a boat this big, and these three big dudes got in the boat, and the boat held. They used rolls and rolls of duct tape, and it floated them. So it was pretty impressive as to how much cargo the boat could actually carry. So that's our question here. And we're going to assume that the boat, the simplest model would just be a rectangle. It would be pretty hard to paddle, but for us in this question, calculating the volume will be pretty straightforward. So how much cargo, meaning weight, can the boat carry? And the bottom line is that when we're considering how much weight it can carry, this is, the weight of the cargo has to be equal to the weight of the water displaced. And so this is assuming, here's our water. We're assuming that the boat, this would be terrifying, right? We're assuming the boat's like this. And so there's no water inside. And you are in there paddling. And here's your paddle. Oh, it's a curved paddle. I don't know how that works. But anyway, so there you are paddling along, and the boat and you are almost submerged, but not quite. All right? So the weight of the cargo is equal to, and that would be the weight of this much water. And remember, water is heavy stuff. So I took a look at this and just sort of approximated the dimensions. I said half a meter and 1.5 meters, and then 1 meter wide, and that's about what those that's about what those boats were. So here's a diagram, and first let's see. So what's our buoyancy? Well, we need the volume of the boat, right? Because if the boat is sinking just up to the surface of the water, it's this much water that's actually displaced. So it's 0.75, 3/4 of a cubic meter. And if we look back at what we learned previously, so the weight of the cargo is equal to the weight of the water displaced. So this is density of water, volume of water displaced, and acceleration due to gravity. I'm going to write that out. So this is density of water. And you're thinking, what is the density of water? Remember, it's 1,000 kilograms per meter cubed. Heavy stuff. Volume of water displaced, and acceleration due to gravity 9.8. I suppose you could build a pool on the moon and do this, and you'd get different values. Ha ha ha. Alright, so what are we doing? Weight of cargo equals rho Vg. Weight of cargo, rho Vg. So, density of water, 1,000. And I'm putting units in here just, sometimes when I look at this equation, I think, gosh, I don't really believe it. I don't know if these values make sense. So I put the units in there to make sure that they're canceling out and stuff. Density, kilogram per meter cubed. Volume, meter cubed. acceleration due to gravity, meter per second squared. So meter cubed cancel, and I have units of kilogram meter per second squared, and a kilogram meter per second squared, kilogram meter per second squared, this is units of mass times acceleration, which we know is force. So this is a Newton. That would be a good thing to have in your notes. And look at this number. So we got 7,350 newtons. And remember, 5 newtons is approximately 1 lb, 1 pound. So I divided that number by 5 and I ended up with this. That's a lot of pounds, okay? So we're just talking about students, right, sitting in a boat. If we look back at this boat. So imagine putting 1,700 pounds of students in there, right, and they'd all be standing up and paddling, and I don't know, how many students would that be? That would be a lot. Okay, so the volume of the boat was not the issue. The fact that it's made out of cardboard, that would make it difficult to get that many students in there and have them not sink. Okay, now things are getting a little crazy. Get out of there. Alright, so, well, I guess that's it for our calculation. So again, that was how much cargo can the boat carry. And we're going to do a lab that's similar with smaller containers, unless you want to build boats and take a field trip out to Crowley or something. Okay, second type of buoyancy calculation. What is the apparent weight of a submerged object? So apparent weight, I think we talked about, we heard this term when we were talking about elevators. So the student goes into an elevator and stands on a scale, and as the elevator accelerates upward, they feel heavier, so the reading on the scale would increase. So apparent weight is how much a scale reads, but isn't your actual weight. So you can imagine this situation. We have one of our 1 kilogram masses, and we hang it from a spring scale, and the spring scale would say 9.8 newtons when it's just hanging there. Then when we submerge it in water, okay, the mass is going to sink, meaning it's not going to float, because it's definitely more dense than the water. But because there's some buoyant force pushing up, the reading on the scale will be less. So what we're looking for here is what's going to be the reading on the scale when the thing we're weighing is completely underwater. So the actual weight minus the buoyant force will give us how much the scale reads. So this would be a good formula to write. Parent weight, actual weight, and if we were to sort of assign some variables, we know that our actual weight is mg, and then the weight of water displaced, that was this rho vg, right, for water. I'll write that, water, and this is our object. Alright, so an apparent weight. Good formula there. Let's take a look at some different densities. So, density of water, we have 1,000 kilogram per meter cubed. Iron, and this is, I was assuming our masses were made out of iron. They might be steel, but I think iron would be cheaper. So iron is heavy, alright. And so, 7.8 times as dense as water. Air, 1.7 kilograms per meter cubed, so it does weigh something, but it's definitely a lot less than water. And then lead is the thing that we think of as being a dense material that's pretty common. Fishing weights, for example, or the keel in a boat. So 11,350 kilogram per meter cubed. Okay. So we are going to do this calculation, and we're going to assume that our mass is made out of iron, and the fact that it's submerged, meaning the reading on the scale is going to be something less than 9.8. Let's plug in. Oh, I didn't solve it. So let's plug in mg. So we have 1 times 9.8 and minus the density of water, which is 1,000. I had these numbers somewhere and I'm looking for them while I'm talking. So if I sound distracted, who knows where they went? Bah! Okay, where's the calculator? Here we go. Okay, density of water is 1,000. Oh, and the volume, so this is the volume of water displaced, which is going to be the volume of the mass. So let's leave that blank for a second, and we'll write it 9.8. So I think that yeah, here we go. So I sort of determined what the volume of this thing would be if we were actually calculating it. We had the radius and we had the height. So, you know, this is a cylinder, right? So circle times the height, area of the circle times height. So in class, when we do this, we can measure this. I am not in class, so I don't have the mass in front of me. So I just sort of work backwards, and let's say that we got this as the volume of our mass. So the 1 kilogram mass has a volume of this. It looks like a small number, but that's because it's in cubic meters. All right. This would be 1, 2, 3, 4, 5, 6, 127 cubic centimeters, which that sounds reasonable. So this number is going in here, and where did that go? Aha! I found it. So after calculating this, we end up with, and maybe you're doing this calculation at home, or maybe you're just waiting for me to find my stuff. Alright, so 8.6 newtons. So that is less than 9.8 newtons. This is what it would weigh if it were just hanging in air. So just hanging. And this is its weight when it is submerged. So notice that it is less, and notice, you see the difference between water and iron? So iron is about 8 times as dense, and so when we put it in water, it lost about 1/8 of its weight. Aha. Okay, so that's our second type of calculation, calculating apparent weight. Thanks for listening.